So I wanted to give a quick overview of these mechanisms. I know that these can be a lot to take in, and an hour and 15-minute class is really long. So I'm going to go back and highlight points that I find the most helpful. So here we have two mechanisms. The one on the left is typically called a 4-bar mechanism, and on the right, it is a 3-bar or crank slider. It can be referred to as both. On the left side, this is 1, 2, 3, 4, or you might have these labeled as A, B with O1, O2. It might, instead of having the O1 and 2, be A, B, C, D, but however this is labeled, you'll have 2 pins on the ground that are fixed with 0 velocity and 0 acceleration, at least for this class. These constraints will typically be here. And one of these bars, so let's say that this is point A and point O, will have an omega. Oftentimes, this initial omega will have a constant angular velocity, meaning that there's no angular acceleration on that first bar. This is often seen as like the input machine, so it's ever causing motion. There'll be some kind of moment on here to make a positive or negative, but constant angular velocity. So this is our AB and AB. It will cause us to have an angular, not AB, AO. AO and AO. It will cause a constant, or not constant, a changing angular velocity for AB and a changing angular velocity of BO. Notice that I'm not putting these in or like slashes like I do with my R vectors. So I'm not saying that this is the angular velocity of A with respect to O. I'm intentionally leaving this off because the angular velocity of A with respect to O is equal to the switch. So if I was rotating it this way, this would also be equal to AO. The reason why these are both AO is because of the relativity of their central point. The length of this bar is the same. So if I was to separate the bar down here and say that this is A and this is O, and look at our O with respect to A or our A with respect to O. Well, let's look at our O with respect to A first. Saying that we are going to be rotating around this point with some OA, we now have a velocity of O with respect to A equal to omega OA times R O with respect to A. The only change here is the direction of, well, we'll use the not scalar form. We'll use the vector form from now on. So OA crossed with R O with respect to A. So the only difference is the direction of this velocity, this direction vector. This value is going counterclockwise, which is positive. If we were to redo the system and have it counterclockwise, so that instead of RO with respect to A and going in that direction, we had instead a vector of RA with respect to O and RAO up here. The velocity of A with respect to O will be AO crossed with A with respect to O. This angular velocity is still going counterclockwise, therefore it is still positive, but the sign of these are different. They're multiplied by a -1. So that's why you know the direction of velocity. The only constraint for angular velocity is that it goes counterclockwise. It doesn't matter where you put it on the bar. It doesn't matter if you put it at A, it doesn't matter if you put it at O, it doesn't matter which side of the circle you put it on. So if we were to draw arrows in a circle, it doesn't matter if I put it this way, or this way. All that matters is that it is counterclockwise. So when you're looking at these mechanisms, thinking about the angular values, I don't have my angular values with respect to anything, because my definition of the angular velocity is that it is positive, being counterclockwise, and it is on the segment of AO. That is a sidebar, but can be kind of confusing, especially as we work from one mechanism to the other. So on AO, we have the positive angular velocity AO, which can also be defined this way. Our AB can also be defined this way. Our BO can also be defined this way, as long as they are counterclockwise, rotating about our segments. I alluded to this earlier, but what is incredibly important for these systems is to have a defined definition for your R length, because the velocity vector is dependent for its direction on the R, A with respect to O. It matters that we have the arrowhead in the correct direction. If I wanted a velocity vector that was O with respect to A, I would use the same angular velocity and cross it with a direction vector that is in the other direction. This is now A with respect to O. So for this, we can call this theta A, theta AB, and for the purposes of this example problem, we'll theorize and say maybe in the given problem statement that B with respect to O is exactly vertical at this time that we were looking at. So all of the directions of the R vectors are incredibly important. When looking at these homework problems or example problems, it's always asking about velocity and acceleration. So you want to jump right into velocity and acceleration. Just be sure you define your directions properly, because that can mess you up later on. So in a problem like this, where you have a given angular velocity and a given angular acceleration for that first length, and let's say that all of the lengths of O1A, O2B, and AB, let's say that the lengths are given, as well as the length of O1 to O2, so this horizontal distance here. All of the position information we can solve for. So we've done our position work. The next segments that you have are velocity and acceleration. With these, we have the multiple segments. We know that we can break these apart because they are two force members. So this is alluding back to trusses. We can solve relative information about their kinematics on each individual ones. Notice that there is a point A on AO and there's a point A on AB. This will come into play later on when we get into Coriolis acceleration. So now we can look at the velocity of A with respect to O, the velocity of A with respect to B, and the velocity of B with respect to O. So these are three velocities, and with these velocities, we can make a relative velocity equation. This equation has X and Y components. With X and Y components, we have two equations, and therefore we can have a maximum of 2 unknowns. This is for 2 dimensions. So when we get to the velocity section, if you have more than 2 unknowns, you can know that you've either missed out on a variable that you needed, or you need to define your dimensions more properly. Maybe you have a theta that's unknown, go back to the position section and solve for your theta. This can be similar to acceleration, as the relative acceleration equation is a derivation of the velocity. So we have the acceleration of A with respect to O, the acceleration of A with respect to B, and the acceleration of B with respect to O. Our relative velocity equation is then this equation. Again, we have X and Y components. There are 2 equations, therefore 2 unknowns. So be sure as you're going through each of these stages to find your 2 unknowns. So let's go back and find the unknowns that are in these problems. But before we do that, I want to break down further how we can analyze this acceleration equation by blowing this part up. So A, O, 1, A, B, B, O2. If we were to analyze the rotation of these in space all by themselves, so not taking into account that other segment, we might think of A with respect to O, that velocity. If this is a positive number, then the velocity would be coming up in this direction. This is the velocity of A with respect to O, because we're treating O as if it's fixed in space. We don't necessarily have to know that it is fixed in space, because all that we're caring about is the relativity of the velocity of A respect to the velocity of O. And we are going to write this out as the velocity of A with respect to O equals omega AO crossed with R A with respect to O, which we've already seen before. But now let's think about what this means in terms of the different kind of coordinate systems that we can express it in. If we have an AO vector with I and J, or X and Y, and this is in Z, we then get a velocity A with respect to O that is in I and J components. But the information we have about our acceleration, once we get up to acceleration, is that there is a tangential acceleration and there is a normal acceleration. A tangential and a normal, where a tangential is a function of alpha and R, and a normal is a function of velocity, or we'll put it as, yeah, we'll go ahead and convert it to omega. So omega cross R. So a tangential is a function of angular acceleration. A normal is a function of velocity, which can also be written as a function of angular velocity. But if we were to calculate a tangential and a normal in these circumstances, we would have our acceleration vector in the a normal, or let's have this set as a normal. So we would have it in the normal direction and we would have it in the tangential direction. This is great for this one problem. The issue comes in when we look at A with respect to B. So this is the velocity of A with respect to B. This is the tangential direction, the normal direction, A tangential, A normal for the segment. There are 2 different directions of your normal and tangential. On AO, our tangential is up and to the left, our normal is down and to the right. For AB, our tangential is down and slightly to the right, and up or to the right and slightly up. In order to add vectors, they have to be parallel. All of the components have to be parallel to one another. So adding these together in the normal and tangential form will not work. This is incorrect assumptions, and the values you will get will be meaningless. In order to circumvent this, we can convert all of these to an X and Y coordinate system. And so we break down our normal into X and Y components and our tangential into X and Y components. So even though we use the normal and tangential direction to quantify what our normal and tangential acceleration are, we quantify them in the form of an X and Y coordinate system. So that's why in a normal and tangential coordinate system, your A normal can equal V squared over R or R omega squared. But if you were to calculate a normal in an X and Y coordinate system, the theory of A normal still exists, but you can't do it in scalar form now because we are now in a different coordinate system. And that's why it becomes omega cross R, because all of these are an X, Y, Z coordinate system. And I mentioned this earlier when I was like, I'll write this in vector form, but this is why you write it in vector form. So the same thing with A tangential. This is equal to alpha cross R, which is true in a normal tangential, but if we were to change to an XY coordinate system, our vector of tangential would have to be omega cross R, where both of these are an XYZ coordinate system. So we're staying in an XYZ coordinate system, but using the ideas of what we learned in the normal and tangential system. And that is because as you move to each of the three segments, the directions for the normal and tangential will be all different. They're not helpful. So we get the components in a neutral XY coordinate system and add them together. So going back up here, we've talked about how you start with position, you solve for A with respect to O, A with respect to B, and B with respect to O in vector form, where this is A and B. And then you can move to velocity, where you solve for the velocity of A with respect to O, the velocity of A with respect to B, the velocity of B with respect to O. These velocities, since we know all of the direction vectors, are synonymous with omega AO, omega AB, and omega BO. And we'll talk about acceleration simplified in a second. So we talked also about how there's two unknowns. In this problem, if we are given omega AO, that means that this is known, and the only two unknowns are this omega AB and omega BO. This is often the case. Sometimes it might be reversed. Sometimes you might be looking for a different kind of velocity. Sometimes they might ask for the velocity in a form of the velocity of B with respect to O, but the velocity of B with respect to O is a function of omega BO. So then acceleration. This is the complicated part, and I talked a lot about how everything is broken down, but I want to simplify it and give a little bit more of a clear map. The acceleration of A with respect to O, the acceleration of A with respect to B, and the acceleration of B with respect to O. We want these in X, Y components, but we need to consider that in theory, we're calculating these X, Y components from the angular velocity and the angular acceleration. So we'll have AO in the normal, AO in the tangential, AB in the normal, AB in the tangential, ABO normal, AB with respect to O tangential. While conceptually we are breaking these down into normal and tangential accelerations, the normal and tangential accelerations have to be in XY components. And that is why the normal will be omega AO cross omega AO cross with R A with respect to O. This will be alpha AO crossed with R A with respect to O. Acceleration, nope. Omega AB crossed with omega AB crossed with RA with respect to B. The acceleration, nope. The angular acceleration of AB crossed with R AB omega BO crossed with omega BO crossed with RB with respect to O. And last but not least, well, maybe least, I don't know, BO crossed with RB with respect to O. So this is often how it's written, but in order for this value not to be zero, you first work omega cross R, and then after you get omega cross R, which you might recognize as the velocity of A with respect to O, then you can cross that with omega A with respect to O. So that's a quick note when you're solving this by hand. Be sure to calculate the right before you calculate the left, even though it's often written without the brackets. Also, notice that especially for AB, pay attention to the direction of your vector, your R vector, because that will change the relative equations a lot if you have these R vectors facing incorrect ways or you reference them incorrectly. So there are a lot of equations here. If your initial acceleration is zero, so AO is zero, that simplifies it down slightly. But even still, these equations can be a little bit time consuming to work out by hand. So I suggest using a simultaneous equation, symbolic solver in MATLAB or Mathematica, maybe Wolfram Alpha. Okay, so we have brought these down into all of their components, but what do we do with them now? And that is where the relative equations come into play. In our case, we have written out A with respect to B and A with respect to B. So our relative equation that I would like to use is the velocity of A with respect to B equals the velocity of, nope, not A with respect to B. A with respect to O equals the velocity of B with respect to O plus the velocity of A with respect to B. And the acceleration of A with respect to O equals the acceleration of B with respect to O plus the acceleration of A with respect to B. And plugging all of these things into these equations, symbolic solver, solve it out. So the biggest takeaway on this first mechanism is that for each relative equation, there are two unknowns. So two unknowns, two unknowns. You must solve for the two unknowns of velocity before you start doing an acceleration equation. You will not be able to solve for any angular velocities in acceleration You need to know the angular velocities before you move to acceleration. And typically there will be one given and then two unknown angular velocities. And from these angular velocities, you can find linear velocities because you know r. For the acceleration, typically you'll have one given angular acceleration and two unknown angular accelerations. These angular accelerations can easily be turned into an acceleration a with respect to o vector because you have a normal already. You already have all of these. And then you can convert your angular acceleration into a tangential, and then you'll do Pythagorean's theorem here. So definitely a lot of work. It is best to keep your pages neat. Even if your handwriting is horrible, try and keep your pages organized with where everything is in order to keep things clear. Also, if you send me pictures of your homework asking for questions, if it's not clear where your work is, I'll ask you to work it out again. So that was the first mechanism and somewhat the most basic mechanism. Let's go back up and look at the mechanism on the right. This is A, B, let's call this A and B. 3-bar mechanism, crank, slider. It is a little bit misleading to say that this is a 3-bar mechanism. Not because, so it's a little bit misleading because you do have some relative acceleration. Breaking this down like we did before, we have AO, 3, A, B, and B here. So we have a velocity of A with respect to O, velocity of A with respect to B, and a velocity of B with respect to O. These 3 variables should be very familiar to you from what we just saw a couple minutes ago. So even though this is a 3-bar mechanism and it looks like there should be less variables, there actually are not less variables because we have the velocity of B relating to 2 separate places. The velocity of B here is connected to A because it is on the rigid body AB. The velocity of B on the slider is relative to the ground. Just like up here, this point B could be connected to A. If you're looking at the rigid body AB, it could also be connected to O2 if you're relating this velocity to the ground. So be sure that you still include all the variables that are required. The really, really nice thing about a slider, though, is that any angular acceleration, angular velocity is equal to 0. So it's moving in a straight line. And typically, not always, but typically these are going to be given to you along the X or Y. And if it's not given to you along the X or Y, the angle will be very well defined. So we have velocity, A tangential, A normal is equal to 0. A tangential is linear, so we can connect that more with rectilinear motion. No rotation. That means that this is not helpful when calculating the angular velocity, and also means that this is not helpful when calculating the linear velocity or linear acceleration because they're inherently wrong. There's no truth in those equations. Instead, what you can use when you have a slider or part of the object traveling in a straight line is to say that the vector of B with respect to O is equal to the magnitude of B with respect to O, and then whatever direction it can travel. So this is not constricted in the X and Y. It slides, sorry, it is not restricted in the X. So it slides along the X axis. Therefore, we have a unit vector of 1 along the X axis. Sometimes you might see these crank slider mechanisms where the slider is traveling vertically. In that case, let's call this D. The velocity of D would have a unit vector of 1 in the Y direction. The variable B with respect to O, or D with respect to the ground, have different unit vectors, but the variable is the same. The variable is still just that magnitude, because magnitude is not changing direction, and we don't have to take that with respect to what's going on with time. The same thing can be said for acceleration. The acceleration of B with respect to O, the vector in X and Y terms will be ABO, and 1 in the X direction. AD with respect to the ground will be the variable DO, but now in the Y direction. So anytime you see a slider, you should be thankful, because that problem is going to have be a little bit easier to solve. Because you can see here, there's going to be a 0 in the X, and there's going to be a 0 in the Y. So mathematically, it's sometimes easier to solve by hand. So sliders can look more complicated, but algebraically, they are definitely more easy. They are definitely easier. Well, I guess that's also in my mind, they're easier. So these mechanisms are definitely scary looking. Just remember, solve for position, then velocity, then acceleration. If you're feeling overwhelmed in a problem, work on the position, take an hour break, work on the velocity, take an hour break, work on the acceleration, take an hour break. Then we're going to get into the kinetics, and then you'll be done. So don't feel like you have to solve the entire problem in one setting. This is the advantage of starting it early if you can. I know that we don't all have the luxury of doing that. Well, good luck with these homework problems. Hopefully this video helped. Be sure to let me know if you have any questions on it.